In the previous lecture, we had a fantastic insight. We realized that the individual quantum orbital levels of an electron and an atom can be seen by us through the photons that they produce. But I wasn't very specific about what conditions we're going to see those particular photons. It's as distinctive as a fingerprint that they use on a crime scene, but it's for each atom will show a different set of energy levels and therefore a different set of energy level differences corresponding to a different set of photon frequencies. But so far I haven't said, well, yeah, so are we going to see those photons be emitted and under what conditions? That's what today's lecture is about. And this is referring to actually some fairly complicated mathematical derivations, which we will completely skip over. I'm just going to tell you the results. Hooray, the useful results here. And the useful results can basically be boiled down to three basic principles of how photons and matter interact. And they're called Kirchhoffs' three laws. No, I know what you're thinking. I was so excited when I found out that I was going to be working right next door to Kirchhoff's coffee shop. I thought, wow, sorry, it's spelled differently. No relation between the Kirchhoff that discovered these laws and our great coffee shop that we like to patronize. But maybe it'll help you remember them. I don't know. So first, let's ask the question, how are we going to ever see emission lines like I've shown right down here, an emission line spectrum, and I've shown you a few examples so you can see the distinctive fingerprint, for example, that would come if you're looking at helium atoms under the right conditions. You see a red and an orange and a number of blue and green emission lines, only no emission lines at any other wavelengths or frequencies, because those don't correspond to the energy differences of any due energy levels of an electron and helium. Sodium, totally different. This is a very distinctive one. It has a pair of very prominent strong lines right in the orange. This is why sodium streetlights look orangey. Neon has a whole series of energy level transitions with fairly low energy differences that all produce photons at long wavelengths in the red. No blue-green photons at all, and so that's why a neon light looks very distinctly red. It's a combination or blend of all of these different energy level differences. But how do we get an emission line spectrum? First, we have to have the electron get out of its ground state. Get off of its butt and get into an excited state where the electron will have to pick up some energy so that it is no longer sitting on the ground state. If it's on the ground state, can't go down any further, can't give up any energy. So what process could raise an electron out of its ground state? It needs to get some energy put in. Well, the first thing you're thinking about is it could absorb a photon. That's right. If it absorbed a photon of just the right energy, it might knock it up to its first excited state. Higher energy photon at a shorter wavelength might knock it up to even a higher energy level, could excite it that way. But that's not the way I'm looking for here. There's a second way, and this is very important and very common, and please don't overlook it, because it's actually somewhat more important than photons in most real-life situations. Atoms are colliding all the time with each other. And, of course, every time a collision happens, we've been thinking of these as little billiard balls that on a microscopic or atomic scale are perfectly elastic, but that's not exactly true. On a quantum mechanical scale, a collision between two atoms could result in transferring a little bit of kinetic energy between the two particles into atomic energy of an electron. So the total kinetic energy before a collision could go down a little bit. If it goes down by exactly the right amount, that quantum packet of energy, of kinetic energy, could be converted into the energy to jump an electron up, to excite it, if it takes exactly the right amount of energy. Now, since collisions are happening millions of times a second with many different velocities, this is as long as there are a lot of collisions around, which there certainly are at densities such as in this office here, then there's a very distinct possibility that an atomic collision will result in an excitation of an electron if, I gotta say this if the speeds, therefore the kinetic energies of the particles which are colliding, are high enough. I think you know what that means. If there's a high enough temperature. Now, actually, it turns out that for hydrogen and helium, for example, the simplest elements, we already saw what the energy levels were, even to just get to the first excited state of hydrogen, for example. Remember the Bohr atom from last time. What is that above the ground state? It's a little bit more than 10 electron volts. Wow. And we just worked out approximately that at room temperature, the typical energies of atoms that are colliding around here, that's kT, was much less than that. Actually, it was only a few electron volts. So this process is not going to work for hydrogen and helium at room temperature. Oh, darn. So collisions will not get them out of their ground state. They're mostly going to be sitting down there in their ground state. All right. Well, but of course we could make a gas hotter. Absolutely. We could run an electric current through it, for example, make a little arc lamp, and then we could get it to glow. And if the collisions are violent enough, to say it's at, I don't know, 1,000 degrees or something in that gas tube or more, then we could excite those upper energy levels of the electrons. And then what are they going to do? As soon as the electrons go up to their higher levels, well, actually, they have a number of choices. Shouldn't say choices. These are dictated by the laws of probability of quantum mechanics. Once an electron finds itself in an excited energy level, it kind of wants to go down, wants to go back down. And there are a set of probabilities that can be calculated quite precisely from the laws of quantum mechanics, basically by the different wave functions, the different shapes of these orbits. And it will have a set of probabilities of dropping down to a number of different, any energy levels below it has some chance that it might drop down there. It might go all the way down to the ground state. It might stop off at a few higher levels and drop down. It wants to drop down by some steps on the ladder, which are dictated by probabilities. It's very much like half-life that we'll see later on with radioactivity. There's a certain set of probabilities, and there's a certain time scale for each of those decays to emit a photon and drop down to a lower energy level to happen. What is the time scale for a typical atom? Well, on human time scales, you might consider it to be quite short. For example, hydrogen or helium gets excited to its first excited energy level. If you just leave it alone, then in something less than 1/1,000,000th of a second, it's going to drop back down to the ground state. What happens when it drops back down? Energy must be conserved always. So it has to give up that energy by, you've got it from last time, the creation of a photon having exactly that energy difference. So in the case of hydrogen, it would give off an ultraviolet photon having 10 electron volts in the ultraviolet part of the spectrum, if you can measure that. Helium gives you off some different things as well. If some higher energy levels are excited in helium, then you can get these pretty emission lines, which are smaller energy differences, small enough to see in the visible part of the spectrum. Your eyeball is sensitive to the visible part of the spectrum. So that's the process. And of course, you might think 1/1,000,000th of a second is a very short time, but actually not so if you're an atom. If you're an atom, that's a pretty long time. That corresponds to millions of orbits of the electron, quote, around the nucleus. Okay, I know it's not really going around, but that's a very long time for an atom to be sitting there with an electron orbiting around it. And the rates, the times depend, as I said, on the details of quantum mechanics. Some, these are called transitions, are very probable and might happen even more rapidly. That may be in 100,000,000th of a second. Others are less probable and might take, as long as 1,000th of a second. That's like an eternity for an atom. All right, so that is how you get these beautiful emission line spectra. It helps to have a hot gas that is being, the collisions are very energetic and violent between the atoms, so that these higher orbital electron energies will be excited easily, and then they will drop down, giving you this beautiful spectrum. All right, so that's one possible case. Then that's Kirchhoff's first law. What are the conditions for so you need a fairly hot, low-density gas, and you will get an emission line spectrum which only has the distinctive signature of the atoms that are present. Now, of course, if helium and sodium were present together, you'd see all of these emission lines together. It'd be an interesting kind of a forensic challenge for you to figure out what the different patterns are that you're trying to match. Hey, Sergeant, there's 2 fingerprints on here. Yeah, well, I'm sure that the police can figure out if there's 2 fingerprints, and obviously atomic spectroscopists can do the same thing. Now, I'm not mentioning right here, but I better tell you, since so much of our world is, especially in biology, is made up of molecules, molecules also have electron energy orbits, which will change, and when they're excited, which can happen quite easily at room temperature, they will also give off emission lines. So we're not just limiting this to helium. Well, I don't care about helium. I mean, that doesn't have chemical reactions with anything. That's okay. All kinds of molecules will give distinctive fingerprints that we'll want to use. This makes atomic and molecular spectroscopy one of the most valuable tools that we have in our entire arsenal. The beauty of this is the information is carried by photons that in many cases, you can actually see, even if the photons, I have to point this out, even if the photons are traveling incredible distances through a vacuum of interstellar and intergalactic space. I can still tell you what the gas composition was of a star or a gas cloud, even if it's sent its photons across 10 billion light years in some cases, which is what I do. We just need a big enough telescope to detect and measure accurately the frequencies of those photons, and I'll tell you what the gas is made of. Quick answer, it's probably made of hydrogen with traces of other stuff. That's helium and then the heavier elements. Anyway, that's just a little sort of inside thing for astronomers there, which you guys are not. All right, what about another condition? For example, suppose we have a very dense gas, such a dense gas that as soon as an emission line is produced by this method, it has a very strong chance of running into another atom and getting absorbed again, so that the electrons might drop down to a lower level, but then the next millionth of a second later, they'll jump back up. So photons are being absorbed and emitted at a furious rate. That's actually a more common situation because we have very dense objects around here with lots of atoms packed together. Then what kind of a spectrum are you likely to get? Totally different. What actually happens, particularly if there are high densities, is not going to tell you the details. These lovely little individual emission lines will get wider. They'll blend out and they'll all blur together into a continuous rainbow spectrum. And there it is illustrated. And this was described by Mr. Kirchhoff in his second law. Whenever you have an object which is opaque, for example, a very high density object, like a sheet of metal, like the walls of my office, like my hand, for example, then it doesn't matter what it's made of. It doesn't matter what the individual atoms are, because there's so many of them. They're furiously emitting and absorbing photons. They eventually come into an equilibrium where they give off photons at all different frequencies, as you can see here, from the shortest frequencies that your eye can see up to the shortest wavelengths, highest frequencies, down to the longest wavelengths, low frequencies that your eye can see, and quite beyond that also, going out here beyond the red, the infrared, and possibly going here above the violet into the ultraviolet, even if we can't see them. So that looks pretty complicated. But don't worry, actually it's quite simple, because under general circumstances, the continuous range of photons that's emitted here, the intensity of those photons, is described by a relatively simple mathematical formula, which I'm not going to tell you what it is. It's called Plancks Law. Same Planck that we ran into before in quantum mechanics, revolutionary of the early 20th century quantum mechanics. He predicted the spectral shape of this continuum emission as a black-body curve. And it depends only on the temperature of the material you're looking for. Just the opposite of the situation I had before with emission lines. It doesn't matter at all what it's made of. Every opaque object will give you this universal emission, a certain number of watts per square meter, but at different frequencies depending on the temperature. Let's look and see in a little more detail. What is the temperature dependence? Well, there are some Planck black-body spectra. Say that 6 times over. Black-body spectra. All right. And see a very interesting fact here. This shouldn't be too surprising. The higher the temperature of the object, the more power, the more watts per second comes out of every square meter. That makes sense because the higher the temperature, the more kinetic energy of collisions there is between atoms, more chances to excite electrons, more chances for them to give off more photons. And they do. Here's a more interesting thing. Notice what the typical wavelength of the photons is. It goes down with increasing temperature. And here's an actual formula. It's Wien's displacement law. Just looking at the peak here. So you can see, yes, there's photons in the ultraviolet here. There's photons in the infrared. But if you're looking, for example, at a 6,000 Kelvin blackbody, wonder why I picked that one, then you see that the most typical photons coming out are around in the green wavelengths here, about 5,000 angstroms or 500 nanometers. And then systematically this peak, first of all, everything goes up at a higher temperature, but the peak also shifts to higher frequencies. So there's a 12,000 degree blackbody. And then if you double the temperature again, the peak frequency of photons coming out doubles again. So the frequency of the photons that are most typically coming out of a blackbody goes up with the kinetic energy of the individual atoms. It stands to reason. Higher frequency photons generated by higher energy materials. And here's our formula. I want you to know this Wien's formula. The wavelength at which the thermal radiation, I'll use that interchangeably, the blackbody radiation peaks, is 0.3 centimeters divided by T. What do I mean by T here? Clearly, this must refer to the absolute temperature of the gas, so I want to measure this in degrees Kelvin, where 0 is absolute 0, obviously not Fahrenheit or some dumb scale like that. So if I give it to you in Fahrenheit, you'll have to convert into absolute Kelvin units. Remember, that's a centigrade scale that starts at 0 instead of at freezing point of water. All right, so now I'm going to ask you two examples that I want you to figure out. First of all, let's go back one slide here. The surface temperature of the sun is about 6,000 Kelvin. So the sun is approximately described, if you look at the photons coming out at all energies, it's approximately described by a black body at 6,000 degrees Kelvin. If I use my Wien's formula here, I divide 0.3 centimeters by 6,000. Geez, what is that? That's like 1/20,000th of a centimeter. What wavelength is that? 20,000th of a centimeter. 500 nanometers corresponds to green light. As I showed you, or maybe yellow light, as I showed you on the previous graph. So that's kind of convenient. That the typical photons that the black body like the sun produces happen to have the frequencies and wavelengths which correspond to our most sensitive vision. In fact, our eyes, as you know, because the pigments inside back there, are extremely sensitive to just a very limited range of frequencies and wavelengths, right centered around 500 nanometers, plus or minus like 50%. Isn't that lucky and nice that the light that our star mostly produces is exactly the light that our eyes are optimized to see? Think it's a coincidence? Of course not. That's natural selection and evolution working. That's why most animals around here are sensitive, especially to the most common wavelengths of light that the sun produces. What's the point of developing, a really good ultraviolet or X-ray vision? It would be, there's just not enough photons around here from our star. That would be very useful for life that would evolve and develop on a planet going around a much hotter star. Then I can predict for you that if they developed eyesight, which is very useful for animals, it would probably be more sensitive to the ultraviolet part of the spectrum. But for us, it's going to be the visible part of the spectrum. So that's a simple one. Now here's a more interesting one so everybody knows what sunlight looks like. It's flooding in my office right now. What about at room temperature? That's not 0, remember, because we're on a Kelvin scale. It's about 290 or almost 300 degrees in here right now on a Kelvin scale. And I just told you that according to Kirchhoff's second law, there is a universal black-body thermal spectrum of radiation, of photons of all different wavelengths, being emitted from every object in this room. Oh my gosh, that's kind of creepy. Except you can't see it. Look, I see, oh, don't look at that. That's a mess back there behind me. You can see all kinds of photons back there. No, you're not seeing the thermal photons from those 300 Kelvin blackbody objects, such as my walls here, for example. You're seeing sunlight and room light reflected off of them, and they're particularly, like that wall is particularly good at reflecting pretty much all wavelengths. It's a very neutral color. That's what we have in our UCLA offices here. So it pretty much reflects all visible wavelengths fairly equally well. Whereas, I've got a little yellow notebook there that has some dye in it or something, which you might think is going to harm your health, but don't worry about that. And it absorbs red and blue photons, but it reflects yellow photons from the sun. That is not what I'm talking about at all. Forget that. Plug into the formula here 300 degrees. So 0.3 divided by 300, I guess that's 1,000th of a centimeter. What is that? That's 100th of a millimeter? Aha! That would correspond to infrared photons. Ah, so you can't see it. Actually, if we turned out the lights in here so there was no sunlight, everything would still be 300 degrees. It would still be radiating infrared radiation, pretty healthy infrared radiation, if only we had an infrared camera. Then you would see that everything in here, especially my skin because it's a little bit warmer, is glowing. In the dark it's glowing, and that's the idea of night vision. Or if you're basically measuring infrared, or heat is sometimes called infrared radiation, and you'll see that everything in this room really is glowing because of its own thermal emission. All right, so those are two examples, and of course, if I tell you a different temperature, then you can just plug in this formula. All right, so that is true of all opaque objects. That's how we get these continuous rainbows of many photons, but especially concentrated within about a factor of 2 or so of the peak given by Wien's law. All right, now let's suppose, for Kirchhoff's last law, his third law, let's suppose that we already have a large number of photons already present, such as sunlight, for example. Oh, by the way, the only other thing in this office, if it was dark at night and the sun wasn't around, what's the only other thing that's hot enough in my office to produce visible photons that I can see, somewhere between the red and the blue part of the spectrum? Ah, there's only one thing that I can get that hot as an opaque object in this office when I run an electric current through a metal filament, particularly a tungsten filament. So that's how lights work. You get them so hot that maybe the temperature might be 1,000 or 2,000 degrees, so that they give off a bit of visible thermal radiation. It doesn't matter exactly what they're made of, whether it's tungsten or carbon fiber or some other kind of alloy. They'll give off a rainbow Planck thermal spectrum. The main challenge, of course, on this, and you can read about this with heroes like Thomas Edison and so on, who really was just a very pragmatic guy, was finding some substance which won't just vaporize and burn up when you keep it that hot for 1,000 hours, or however long these light bulbs are supposed to last here. So that's how that's how old-fashioned light bulbs used to work. You just have a hot filament and you're looking at the opaque radiation, the blackbody radiation from it, and you got to keep it pretty hot. All right, so now we've established that we have lots of photons of all different frequencies. Now, suppose you have a source of a lot of photons of all different frequencies. Now, let's put in some atoms of your choice, which are less hot, maybe cooler atoms. What could happen? Well, I already have a huge supply of photons offering little packets of energy at each different frequency. Smaller amounts of energy here, more packets of higher energy here, higher energy, and even like twice the energy packets over here. But each one of these photons is a distinctive packet of energy, you guessed it, which could correspond to an energy jump between two energy levels of an electron in some atom. Suppose we had hydrogen atoms, or sodium atoms or something like that. So there's a great prospect, if we have a lot of photons, that just the particular photons of the particular frequencies corresponding to the atoms of gas that I have present could get absorbed. The others will pass through unmolested, not affected at all by the gas. So what are we going to have? In such a case that I've just described, a flood of photons from a hot source shining through a cooler, thin gas, only a particular distinctive fingerprint of dark absorption bands will be imprinted on the spectrum, because only those particular wavelengths, like one there, a few there, two big ones, oh, you can't see that, yeah, down there. So on only these particular wavelengths carry exactly the right energy to absorb, to excite an electron from a lower level to a higher level. Now, like I said, the gas could be cold. Why did I say that? I mean, a cold gas, that means that all the electrons, almost all, will be sitting down there in their lazy ground state. Okay, could I have an absorption line spectrum if the gas is cold and it's just in its ground state? Yep, because even in the ground state, the electron has many different energy levels that it could go up to if only it were given a photon of exactly the right energy, exactly the right wavelength. So this is exactly what happens, for example, to give you one classic example, in the upper layers of the outer atmosphere of the sun. You have a very hot source of photons inside the sun. It's producing red, green, blue, yellow, violet photons, and they're streaming out of the sun. And then, as they pass through the last few thousand miles of the upper atmosphere of the sun, it's relatively lower temperature, and the gas is very thin, and it imprints these dark bands. In fact, I'm showing you here, this is not an artist's conception. This is an actual observation of a solar spectrum. You see all those little dark bands in there? How cool, it's kind of a pun, is that? Each of these dark bands here is a fingerprint left by some atoms in the upper layers of the sun's atmosphere, which allows us to figure out what the sun's upper atmosphere is made of and work out the conditions in it. It's really brilliant, even though nobody is going to be going right into the sun to take a sample. We have a remote sample here that tells us what it's made of. For example, these two violet photons down here are produced by calcium nuclei. Let's see, that red one there is produced by hydrogen. Expecting that one to be pretty significant in the sun. And there's some others here. In the blue-green, we have some absorption caused by magnesium atoms. There's even one absorption here due to CH molecules. Wow, amazing that molecules can barely survive in something as hot as the sun in its upper layers. All right, so actually, they're almost everywhere you look, there's some weak absorption here. The strength of the absorption, how black it will be, will depend to some extent on how many of that particular atom is present in the sun. So that would be useful also, and some other effects, like how intrinsically strong is that particular emission line for a given number of atoms. But you don't need to know any of that stuff. So Kirchhoff's third law, to summarize, it says when you shine a continuous spectrum through a cool, thin gas, the gas will impose a whole series of absorption lines, which do depend very much on the chemical composition, what atoms and elements are present. In fact, for every one of these absorption lines that you see here, these correspond to the same wavelength that in Kirchhoffs Law 1 was an emission line. The emission lines are at the same places, because it's the same atoms, but they've gone into absorption. Now, either way, we have a fantastic opportunity, whether we're using emission line spectroscopy of something hot, or whether we're using absorption line spectroscopy with a bright light source behind it, we have a chance to figure out detailed atomic information about the composition of this gas that we're probing, and that is what is so unbelievably useful. So I like this slide because it shows the interconnectedness of Kirchhoffs laws in three different cases. Let's see. Here is a very hot light source. This could be like a tungsten filament that's like 1200 degrees in a lamp, or this could be the interior of the sun. It's producing a rainbow continuous spectrum. So if you look directly at this, you run the light through a prism, which, as we all know in Physics 6c, spreads the wavelengths out, the blue wavelengths bending more, the red wavelengths refracting less. And so That's your continuous rainbow spectrum. However, we also happen to have nearby a thin cloud of gas. Okay, hotter or cooler depends on what you want to look at. It's not at low temperature. It's just not as hot as my light bulb. So if I were to only look at the thin cloud of gas with no background light source, in other words, suppose I were to look at it from this angle down here. So I'm just looking at a thin cloud of gas. There's nothing behind it. There's no visible photons coming at me. No continuum of photons coming at me. I'll see an emission line spectrum here. Here's the intensity versus wavelength, and you see only 0 except at particular spectral line features which depend on what atoms are present in this gas, which electron energies have been excited and they drop down to lower energy levels, yielding an emission line photon. However, the most complicated picture, which I say for Kirchhoffs' third law, is what if we're looking at the hot light source? This is our yellow observer over here horizontally. We're looking at the hot rainbow source of a spectra of all kinds of different wavelength of photons, but it passes through this thin cloud of gas. Then notice we see photons everywhere. That's our original continuous spectrum, except there are some of them missing. They're dark bands. Some, maybe all of them, maybe a little bit of them missing here. Dark-ish absorption bands. And notice the thing I want you to see about this slide. The wavelengths of those absorption bands, because they depend on what atoms are in here, are the same wavelengths as we previously, this observer, saw the emission lines, because they correspond to the same fingerprint of energy levels of these particular atoms. See, this whole pattern is basically now gone from emission into absorption, and it's repeated here. It's a distinctive fingerprint of what that cloud is made of. All right, so that's all you need to know about Kirchhoffs' laws. Now I have one other application to give you here, which will be in the next mini lecture.